Hello and welcome to the channel All Things Calculus. My name is Beth Dorsing and I'm excited to walk you through some free response questions. Now for each of the free response questions that we're going to be taking a look at, there's some materials that you're going to need that are linked in the description. The first is going to be the AP free response tips and info worksheet. This is a packet that summarizes all the different types of free response questions that tend to show up on the AP exam. I like to call it the How to Make Your AP Reader Happy info packet. You're also going to need a copy of the question for each of the videos. Those are linked in the description. You can print them out or have access to them and just do them on your own paper. And finally, you're going to need access to some sort of calculator for any of the calculator active questions that we have. I prefer Desmos, and all of my videos will show you how to use Desmos to answer these questions. So let's get started. Welcome to the particle motion problem. This is going to be another classic velocity type problem. It is a calculator active free response about linear motion. So you'll need access to Desmos or a TI-84 of some sort. We're going to be looking at velocity, position, and acceleration, how they're related. We're going to review how to describe the motion of the particle, whether something's moving left or right. We're going to have a conversation about what displacement is, total distance traveled, how to use displacement to find a new position in time. And we're going to take a look at this problem. We're going to talk through how to solve it. And then at the very end, you'll see a little wrap up with some tips and some tricks for how to maximize your points on a free response question about linear motion. So let's get started. Now, the first thing you're going to make sure of is that you have a good version of Desmos open, and the website is great, but to get the most accurate version of Desmos that's going to be available on the AP exam, you're going to want to go to desmos.com/testing, and then if you scroll down, you'll see all the tests that have Desmos embedded, and you can use the various versions with various capabilities enabled or disabled depending on the exam. And you're going to go to College Board, and you're going to click on the graphing calculator under the College Board, and that will open up a Desmos version that you can use. Now, this will already be defaulted to radians, which is wonderful. It's not going to make too much of a difference in this problem, but it's good to know there are never degrees in AP Calculus. So let's take a look at the problem. We've got a particle moving along the x-axis so that its velocity at any time, t greater than or equal to 0, is given by this equation. Now, my first step before I even solve anything is I want to type the equation into Desmos. And when I type it in, I want to make sure that I'm doing function notation. So I'm going to type in v of t equals, I'm going to type the whole thing, t cubed minus 4t squared plus 3. Now, we've got our equation in there. We've got the graph visible in Desmos. I like to change my graph over to projector mode. It just makes things a little bit bolder and easier to see on the screen. So part A, there is one time t equals t sub r in the interval from 0 to 2 when the particle is at rest, in other words, not moving. Find t of r for t between 0 and t of r. So we want to find t of r. We want to find where the particle is at rest. And we want to know for the interval, it's a little weird, it's cut off, hard to read. So for that interval, is the particle moving right or left? Give a reason for your answer. Okay, so in order to figure out if a particle is at rest, we need to recognize that that means that it's stopped. The velocity of the particle at that time is going to be 0. Now, anytime I think something, I write it down. So I'm going to write down v of t needs to equal 0. Right there, that tells my reader what am I looking for on the graph. So now I'm going to come over to the graph, and I'm only concerned with positive values. So I'm going to set my zoom, and you guys, if you can pinch your screen, if you have a touch screen, it's real easy to zoom in and out. You might need to go to your little wrench and adjust the viewing window if you don't have a touch screen that you can easily pinch and zoom in and out on. But if I kind of zoom and see what's going on here, I can see that my velocity is actually 0 in 2 spots. These are my x-intercepts, and that's what I want to look at when I'm looking for where the velocity is 0. So if this is the velocity curve, the x-intercepts are what I'm going to look for. Now, it does bound me to looking between 0 and 2. So that second value of 3.791, I'm not going to worry about it because it's not in my interval. But I am going to worry about t equals 1. Now, I probably could have found this without the use of a calculator by taking that equation and just simply setting it equal to 0 somehow and doing some fancy algebra, it might have been possible, but we've got a calculator, so this is what we're going to go with. So the velocity equals 0 when t equals 1. Now, it says for the interval, so on the interval, 0 is less than t is less than 1. So remember, so t sub r is equal to 1. That's what we're saying is our answer. So on this interval, we want to know, up until that point, what direction are we moving? So I'm going to go back to my graph, and I'm going to see that prior to 1, the graph of my velocity, so that would be this area right here, from 0 to 1, it is above the x-axis. And so when we're above the x-axis, that means our velocity is positive. So on the interval from 0 to 1, v of t is greater than 0. You can also just say it is positive. So the particle is moving to the right. So good concepts to review. Generally, positive velocity is right or forward. Negative velocity is going to be left or backwards. So those conventions are just generally widely accepted, and that's kind of how we know what direction we're moving. So now let's look at part B. Part B says find the acceleration of the particle at time t equals 2. Show the setup for your calculations. Is the speed of the particle increasing or decreasing at time 2? So to find acceleration, you need to know that acceleration is simply the derivative of velocity. So I'm going to write that down. If I think it, I write it. So the acceleration at time, or you can say a of t, I'm just going to go ahead and say the acceleration at time 2 is v prime of 2. And I want to just establish that. I take nothing for granted. I don't assume that my reader thinks I know things. I want to make it real easy for whoever's reading my FRQs to give me my points that I deserve because I know things. So I'm going to type into Desmos. I'm going to go v prime of 2. And it's going to spit it out, -4. Now, the next thing it wants me to know is the speed increasing or decreasing? In other words, am I getting faster or slower? So in order to know that answer, I also need the velocity at time 2. And again, super easy to find it in Desmos. V of 2 is -5. So now I have a velocity of -5, and I have an acceleration of -4. And so whenever I have a velocity and an acceleration that have the same sign, this means that my particle is getting faster. So think of it this way. They're forces and they're acting in a certain direction. So if the velocity says that I'm moving to the left because it's -5, and the acceleration is also a negative value, that means acceleration is also working in the negative or left direction. Think of acceleration like a push. So if my velocity has me moving left and I get pushed to the left, I'm going to get faster. However, if they have opposite signs, that means that my velocity is moving one way, but then my acceleration is moving the other way. And when you have two things acting in the opposite direction against each other, that's when we have a particle that's going to slow down. So here's how I'm going to construct my response. First of all, I want to record these values on my paper because these values will earn me a point. So I've got the two values on my paper. And so now I'm going to explain my reasoning. I'm going to say why I know that this particle is getting faster. So I'm going to say the particle is speeding up, or the speed is increasing, because a of 2, now don't say a of t, say a of 2. You have to say the exact time. A of 2 is negative and v of 2 is also negative. You don't have to say less than 0. You can use the word negative if you want. This is just the mathematically accurate way of communicating this. All right, let's keep going. The position of the particle at time t and its position at time t equals 0 is x of 0 equals 5. Find the position of the particle at time 3. Now, in order to find the position at an instant in time, you need to know where you started, and then you need to know how far you've moved. So we know where we started. We are starting at 5 because at time 0, we know that it says our position's at 5. So in general, we're going to use this formula where we say the position at time B is the position at time A plus our displacement. And now the displacement is the integral from A to B of velocity. Anytime we integrate a rate, it gives us the amount of change. So if our rate is measured in, units per minute or meters per second or miles per hour, and we integrate this rate, we are going to get the miles traveled or the meters traveled or whatever we're measuring, the units traveled. So an integral always tells us our displacement when we're talking about if we integrate velocity. So in this case, this formula earns me 0 points, but it gets me started and on the right direction. So here's what I'm going to do. At time 3, that's the position I want. So I want the position at time 3. So I'm going to take the position at time 0, and I'm going to add to it the integral. Now, a good little rule of thumb when you're using this formula is to not get stuck with the numbers being, having to be 0 over on the right side with the integral. What I like to generally think of is, okay, sometimes my integral, the limits don't have to go from bottom to top. It's nice if they do. It's easier to understand. But remember, if the limits are ever backwards, like you have the bigger number on the bottom as your lower limit, all that does is change the sign of the integral. So in our situation, I always tell my students that when we set up my limits, whatever I have here, that is going to be the lower limit of my integral. And if I just remember that those two red numbers have to line up and match, then it removes some of the thinking that I have to do, and it ensures that I'm going to get the right answer. And it's always going to then be adding the integral to the starting or the known position. So now I'm going to type in, or I'm going to write in v of t dt. And this right here is all I need to write to show my work, because now when I go to Desmos, I literally am just going to type in the numbers. So I know that x of 0, I know that this number is 5. So in Desmos, I'm going to go 5 plus, and then to get an integral, I type int, and then I go 0 to, let's see, oh, and it's not 5 up here. I miswrote. I had 5 on the brain. This upper limit needs to be 3, not 5. So let's make sure we're doing that right. So that's going to be the displacement from time 0 to time 3. And then in the integral for my integrand, I'm just going to type in v of t dt. And that gives me my position at time 3. So I'm going to record that. X of 3 equals negative 1.75. And that right there is enough information. I've shown an integral, I've used my initial position, and I've got my final answer. And usually on a problem like this, what we have shown with our formula, using that, x of 0 equals 5, having a displacement integral from 0 to 3 of v of t dt, that along with that final answer is going to earn me all of my points. So now the last part here, part D, it says find the total distance traveled by the particle over this interval 0 to 3. We're going to show the setup. So now total distance, here's what's happening. If I kind of go back and I look at what's going on with my graph, sometimes my velocity is above the x-axis and sometimes it's below. And when it's above, we're moving in the right direction, and when we're below, we're moving in the other direction. And so what happens is your displacement just measures the difference between where you started and where you end. It doesn't measure where you've gone in between. So what we want to do is we want to make sure that any negative velocity that we have gets made positive, because then we can combine it and say, well, now we are going to measure all the steps in between, even if you went back and forth, back and forth. So think of it like this. If you go back and forth from your house to the store, generally when you make a trip to the store, your displacement will be 0, because you'll go to the store and then you'll come back to your house. So your displacement is 0. The amount of change from your start to your end is 0. However, if you look at your odometer on your car, the number of miles you traveled to get to the store, that's going to be your total distance. So it doesn't take into account the cancellation of one direction and then completely backtracking and going back the complete opposite direction. So displacement in that case, you'll have some distance canceled, but total distance is all going to be positive. So the way that we set this up is we make an integral and we go 0 to 3 and we integrate velocity, but we put absolute value around it. And there's the setup. And then in Desmos, it's going to look a little bit like this. You're going to type in int, and you're going to go 0 to 3. But then you're going to do an absolute value. And the way you access absolute value is right above the enter key. There's a couple different ways. There's a little key that has like a vertical line, so you can type that vertical line. You can also go down. There's a little keyboard icon at the bottom of Desmos in the bottom left. And when you click it right above ABC, you'll see the absolute value. You can actually type in the command ABS parenthesis and then do V of t in there, and that will bring up absolute value. So you've got a couple different ways to access it on your screen. And then you close off your absolute value dt, and this spits out my total distance traveled. It makes everything positive. So we're going to have 10.583. And that is going to be enough for my total distance. So here is a snapshot of everything that we just did right there. And all the points that we would earn, hopefully, on a free response like this. So let's move on. Let's talk about some tips and strategies and kind of generalize these problems and record some info about how to do these linear motion, particles in motion problems. So in general, when we are looking at linear motion free response questions, they're pretty easy to recognize because in the problem, something is moving. Usually we're given some sort of velocity equation. We're asked about motion, direction, position, total distance, acceleration, position, things like that. They're just going to be a part of the problem, and they're very easy. It's very easy to tell if it's a velocity equation. So how do we approach it? Well, my first steps are going to start out with, if it's a calculator active question, make sure that you type the equation in its entirety into the calculator. Whether you're using a TI-84 and you go to Y1, take your time, type it in. In Desmos, don't forget to type it in as V of t equals, or whatever the equation is. Now, to find, when you're reading it, if you're given an initial condition or initial position, make sure that you record that on your paper, record the equation on your paper, and make sure that you're recording it correctly, especially with these digital hybrid exams. A couple reminders that V prime is your acceleration. So when you take the derivative of the velocity, that gives you your acceleration expression. Your position is going to be the antiderivative of velocity. So that might be something we want to add in here as well. So to go from velocity to position, you're going to use an antiderivative. And when you do that, you need to remember to solve for that constant of integration. So if ever you're asked to find an equation or an expression for the position, that's when you do the antiderivative. You have plus c, and you're going to use that initial position to solve for that c value. But this is only when you want an equation. For position. Okay, so other things that you're typically going to be asked for is potentially the displacement. So the displacement is kind of the net movement over an interval. So that's simply the integral from a to b of v of t dt. And remember, when we integrate a rate, anytime we do the integral, if velocity is meters per second, then when we do the integral, we turn into meters. So the units are going to shift, and anytime we integrate, we take away a per time, and anytime we do a derivative, we add a per time. So that's why when we see acceleration is going to go meters per second. So those units are going to shift every time we do a derivative or an antiderivative. Some other things you're going to be asked for is the total distance. That's a big one, and that's simply the absolute value. So on a non-calculator question, you might have to figure out where the velocity is 0, and then any negative values, you might have to set up more than one integral find the integral and the displacement or the distance traveled over any positive velocity spaces. And then any negative velocity spaces, you would take that integral and then take the absolute value of that. And then you can combine all those little sub-displacements, so to speak. We're often asked for a position. So if you're asked for a specific position in time, here's the formula that you want to remember. Your new position. So sometimes this position is after our known position, but your new position, we're going to call that time b, and that's going to be the upper limit of your integral. You're going to take your known position. A lot of times they make it easy on you, and your known position is your position at time 0, but it's just your given position or your known position. And whatever that is, I always make that in this setup, it's your known position plus the displacement. And I always make sure that whatever time my known position is, that's going to be the bottom limit of my integral. And just remember, if your limits are ever kind of feeling backwards, so instead of going from 0 to 5, you flip around and you end up going from 5 to 0, so like you're going back in time, it's okay. That integral will give you a negative displacement because you'll be moving backwards, and it'll all take care of itself. So just simply using the formula as it is going to get you that answer that you need. Now, you're also going to be asked to do a little bit of analysis about what's happening with the particle. So just a reminder that if the acceleration and the velocities have the same signs, that means that that particle is going to speed up. If they have opposite signs, that means that the particle is going to slow down. So how can you tell if you have positive or negative velocity? Well, you're going to want to show the value. So plugging the number in and getting a numerical value is always an excellent idea. So let's add that in. Try to show numerically whenever possible. But in case you can't show it numerically, if you ever have a graph that you can use, on a graph or in general, what we're going to look for is, so the velocity will be 0 at the x-intercepts, and then above the x-axis is where the velocity is going to be positive on a velocity graph. Below the x-axis, if you're looking at the graph of velocity, that's when your velocity is negative. And so positive velocity is generally indicative of moving to the right or forward. Negative velocity is moving left or backwards. And final reminder here, you're going to be asked probably at some point to know if a particle is changing direction. So it's really important to know that you need two things for a change in direction for linear motion. You need that velocity to be 0, and then you need to show a sign change. In other words, you need either on a graph, you need your graph to look like this. So if you have a velocity curve that looks anything like this, and this is t, and this is v of t, you're going to have a sign change here, but unfortunately right here, this is no change in direction. It is a spot where the velocity is going to be 0, but you'll see the velocity stayed negative. So there was actually no sign change or no change in direction that we can show. So the velocity being just 0 is not enough to show a change in direction. You need both the velocity to be 0 along with a change in sign to really prove that you've changed directions. So here are at a glimpse an overview of some tips and tricks for those linear motion free response questions. This is by no means complete. It's just very general. Based on kind of like years and years and years of looking at these tend to be the big topics that show up on this type of a free response. But no matter where you are with calculus, the more you practice, the more free response you're able to find and do, and Google some practice, the better you're going to get at doing these types of problems, and the more successful you'll be on the AP exam. But no matter what, just keep trying, and my encouragement to you as always is you've got this.